let us go into our Q&A session. Let me see. I already have folks who are raising their hands. Let me go to Michael Boyd first. Michael.
Hello. Hey, Steve. So I had some questions. Hold on a second. I put them in the chat. Let's see.
Okay, yeah, and again, just a reminder that you can use Option Y on Mac or Alt Y on Windows to raise your hand during to ask questions.
Okay, you were asking about. I think you answered that actually about refractive index and making repulsive gravitation too. And let's see, the next one I had was the insulator. At the center, would it form a spinning disk?
I couldn't hear you. Can you repeat that?
The insulator, you know, in the center you have an insulator, correct?
Yes.
Would it be forming a spinning disk?
No.
So it's stationary.
It's just an insulator between the two halves of the modified sphere. If you look at a spherical antenna, you have to slice it down the middle, and a lot of how the antenna works depends on the integrity of the electric field across that gap. So you want that gap to be small, and you want it to be insulated, and so that provides the key to making the antenna work.
Okay. Let's see. I had another one. When you talk about positive mass, would that be applying a negative gravitational force as opposed to so positive mass, you mean it has a weight greater than 0, correct?
Yes.
Okay. And so a negative mass would be the opposite, would have a gravitational, it would be weight less than 0, correct?
Well, if you look at the MG plot, you can actually control the weight of the negative mass. If you make it equal to the positive mass, when I say positive mass, what I mean is you reduce the radiation intensity or power so that you're bringing this model out of the mass reduction mode, and you're just making it like the mass would normally be without any radiation at all. So what you're trying to do is you're trying to, on the top where it's positive, you're trying to provide a little bit of radiation to bring it down lower than it would normally be, so you can balance the negative radiation weight on the bottom. But you can control both of them. You control the mass of both of them by controlling the amount of radiation you have from the radiator and the difference and how much you dampen it so that you create a different mass structure in that part of the antenna. So whatever you select the radiation, it's going to select how much negative mass weight you have. And that weight in a planetary gravitational field is just going to fall up, just like it would be falling down with positive mass, only it goes the other direction, it falls into space.
So at one point you said something to the effect of, this has nothing to do with metamaterials, and that made me feel uncomfortable. I would think it has the opposite, that it has everything to do with metamaterials. What made you feel that was the case? Why do you feel it's not anything to do with the metamaterials?
Yeah, I mean, you know, I spent a lot of time fooling around with transmission lines, swapping the, trying to simulate lines, especially with 3D planes, so I can create a volume with transmission lines. And as you swap the L's and the C's on the model, you get negative permeability and permittivity. And there's actually been, there was a guy in Canada actually beamed microwaves at these things, and I could actually see the reflections happening in the ways that it would be meta. So I'm not anti-metamaterials. I just don't need it. As an engineer, I don't look for solutions that look for problems. I try to understand the problem and then try to understand the solution that works for it. And this model just doesn't need negative permeabilities or permittivities. And if you look at what it's doing when it reduces phase velocity, mu's and epsilons are getting larger. So the only thing that this model says is it's equal to E0 mu0 or larger. So the answer to your question is the model doesn't need it.
Okay, I appreciate your answers. Steve, I just wanted to let you know I posted a section from this book, Metamaterials, and it's
in chat. Yeah, I see that in chat.
And I would request that you take a look at that, because it if you look at that, you'll see that it has pretty much, it supports what your hypotheses are that you're presenting. So I really I'm strongly in agreement with what you're presenting. So I'm trying to help you out. Is what.
Well, I'm not married to anything except my wife.
Just take a look.
I'm married to my wife. That's it. Theories I don't care about. They come and go. I've stuck with this one for 20 years because it just gives good answers.
Yeah, no, it should, but the physics is it's a lot of people coming to the same conclusion through different methodology. It's basically what I.
Yeah, there's a lot of theories out there, and I'm not saying that they're wrong. I'm just saying this model doesn't need them.
Yeah. Well, thank you again, Michael. Let me go to Jeremy Reese next. Jeremy.
Hey, thanks, Tim. Thanks, Michael. I have a number of questions here in the live chat. I want to read a couple of those and then get to some of the actually, why don't we stick on Mike's theme first, and I'll ask my question because it kind of had to do with some of this. Have you ever heard of? So you're basically saying that we build an antenna system, and the antenna will work to. I mean, this is like very Jetsons-esque model of how to do the anti-gravity. If I'm not mistaken. Have you ever heard of fractal antenna and fract antenna systems and fractal antennas?
I've heard of them. My understanding of them is that they're broadband because of the fractal nature of them, but I'm by no means an expert with that.
So I was just saying, this is back to Michael's questions. We won't need metamaterials necessarily. You can get the effect without them with, more conventional materials. But what about the idea that, just like in this, we're building an antenna, these fractal antennas have been shown to get much more reception and much more broadband performance. So if we were talking about enhancing the performance of your, model, I don't see why metamaterials wouldn't be something, would be something you'd try to push us away from, because it seems to me like, yeah, we may not need them. They may be expensive and hard to engineer, but the engineering, like the models, they seem to work with the metamaterials that seems to me that they should only enhance any effect that you're reporting with your model should be greatly enhanced by using a metamaterial instead. So we might be able to do a lot more with a lot less energy if we do use metamaterials. But
again, I'm not saying other models aren't credible. I'm presenting this model, and the model as presented doesn't need that concept. But, it needs superconducting antennas. Maybe with metamaterials, you don't need that. I don't know. You're getting into an area of physics now that is involved, and there's a lot of experts in that area, and I'm not one of them. I can tell you that with a transmission line, you can produce zero and negative mass with negative in permeability and permittivities. So I'm not saying you can't do it. I'm just saying that this model, unless you're trying to actually improve the efficiency of the antenna, from the basis of the model, it doesn't need metamaterials. Maybe metamaterials will make it work better.
Well, even if we're talking about, conventional TCP, Cat6 and Cat5 lines, twisted pair, the idea of using a twisted pair is almost kind of like a chiral metamaterial. And it works. It happens that was the best use of long range data transmission through wires. This was developed by scientists at Bell Labs, I believe, and other places. So the twisted pair is essentially kind of like a metamaterial, and that's used everywhere in regular data transmission. That's what we wouldn't be talking right now if it weren't for twisted pair and this technology. I have another question for is this craft a capacitor plate operation? Kevin Andrew asks. I don't think that's it's not quite a capacitor plate. There's more.
Well, it's kind of like that. I can see why that question would arise. A capacitive plate antennas, you typically take an antenna like a dipole wire and you stick a disc on the end of it. That's not what this is. This is a prolate squashed sphere antenna that's squashed into a saucer, and the saucer itself is the antenna. You can also pull it into a cigar, and the cigar itself would be the antenna. If you take the extreme case and you pull it too far, you get a wire or a flat plate. So you're kind of in between those two things with these antennas. And because it's derived from a sphere, I was surprised, but they tend to have natural resonances, which gives you a fighting chance to actually make this thing work without super involvement.
Thank you. And that was Kevin Andrew who asked that question.
Awesome. Now, Jeremy,
Create the Imaginable. One more from Create the Imaginable. He wants to know, what are your views on space-time and how does that affect your research? And that's it.
Yeah,
All I
okay.
got.
Well, okay. What I said in the beginning was this model shows you how to do it, but it doesn't tell you anything about what happens once you do it. Obviously, if you go through the math on this thing, and it depends on which model you choose, kinetic energy, momentum, or whatever. But if you can change several orders of magnitude of mass, let's say if you're going 100 miles an hour, and you change 3 orders of magnitude and it's linear, now you're going 100,000 miles an hour. If you could start out at 100,000 miles an hour, you could get up to almost the speed of light. So when you do that, the Lorentz transformation happens, and now all of a sudden your mass starts increasing because of Lorentz. So you kind of have all that going on in relativity that you'd have to contemplate. This model sort of cuts off right where that starts.
All right.
Awesome. Thank you, Jeremy. Let me go to Molina. So Molina, thank you for joining us. This is your first time at the conference. And I'll ask you to unmute.
Hi. Yeah, so thank you for having me. Yeah, and I was wondering, was there somewhere in there that you said that you would need to increase the frequency in some kind to like amplify what the antenna is doing?
Okay. Boy, I could talk a long time on this. By the way, I'm a Burns also. I actually am a Robert Burns. I go by my middle name. Well, if you study frequency,
Did you used to work at? Were you part of McDonnell Douglas?
No.
Robert? Nope.
No.
Okay, there's another Robert Burns.
No, I'm a rogue engineer that just bounced around startups most of my life. If you study frequency on this model, like I said before, the lower the frequency, the less power you need to affect the mass change or the space refraction effect. You could control. You could set it. You could set it as a constant power, and then you could control frequency to control your mass shift. The problem with that is that you run into the bandwidth of the antenna changing on you, and also the idea of keeping frequency stable is not an easy thing, and you have to keep it really stable.
Mm.
So it makes more sense to me to select a frequency that would be preferably at a resonance point of the antenna, because now it's just resistive. And then you change power to affect it by changing the voltage amplitude of the signal that you're delivering to the antenna. To me, that's a much more effective way of controlling this thing. So my view is you would find a frequency that works well with your antenna, and then you would control power delivered to the antenna to control the effect.
Would any kind of, like I had an idea of if you were to take something like a quartz crystal or some kind of crystal that controls, that resonates, you know, and make it into almost like a gel that could then encapsulate the whole thing and create, I don't know, I guess keep it at a certain frequency or be able to resonate. I am not a engineer like you, but I've just been having these ideas and wondering how they could, if they could be applied in any kind of way of what you're talking.
Well, I mean, there's ideas about how you can do this. If you get on De Aquino's website, you'll get a whole bunch of those. And my suggestion is check his math. He makes algebra errors. And sometimes he makes assumptions that aren't true either. But if you can figure out the validity of what he's talking about, he talks about some just amazing things. And he talks about, I think one of the things he did talk about was crystals. I haven't read up on that, so I don't know exactly what he was saying, but I would encourage you to spend some time on his website and read over some of his work.
Okay.
Wonderful. Okay, well, thank you, Molina. Steve, let me jump in really quick, if it's okay. I'd like to jump in with kind of my own question. So this goes to UAPs and the upshifting of frequencies. And I think this is kind of what inspired your talk, right? And you covered a lot of stuff in this one, but I wanted to kind of drill down on that as well. So again, I think that the discussion point that you started with, this was a few conferences back, was that UAPs tend to show cold, right? Like on the Navy jet radar, they tend to show cold, but then we have this anecdotal evidence of like a really bright glow. And so the idea was that the thermal energy they're giving off is being upshifted into like visible light, right? To create a glow, maybe even hard UV, maybe even X, because UFO experiencers, I guess as they call themselves, sometimes show evidence of burns or radiation exposure. So is that, do you think that that's definitively happening, I guess, or?
Well, I have to say it's an interesting idea, and it connects a lot of dots. Another dot that it connects for me is, I talk about Hill's book a lot. One of the things he had in there was a Geiger counter reading of an object that they were estimating was about about 1 kilometer away. And then he talks about the fact that when it went behind a hill, they actually got a background on the Geiger counter. I spent 10 years of my life designing nuclear instrumentation. The fact that they got a background on that reading, it adds a lot of credibility to me. The problem I have with that reading is that the value that they got, if you apply inverse square law and extract it back to the source, it's a huge amount of radiation. So I spent 25 years of my life thinking that was a bogus measurement. So with the frequency shift model, if it's daytime and you've got ultraviolet around and you're shifting out into X-rays, now you could actually come up with a scenario that could provide that level of radiation that they were talking about. Here's the problem I have with frequency shift. Higher frequency photons have more energy than lower frequency photons. A gamma ray is a lot higher, it's like MEVs, millions of electron volts. An X-rays, thousands of electron volts. ultraviolet, it ionizes, that's why you get sunburn, but it's, you know, electron volts. So if you're going to shift things up, you're going to have to add a whole lot of energy to it. And I don't know where that energy would come from. And to me, that would be pretty much wasted energy. So even though the idea of frequency shifting connects dots, it's not clear to me, A, that it's effective to do that in a design, and B, or that's assuming that you had the choice of whether you would do it or not, and B, you'd have to come up with some incredible power source. I would even say that the power source, almost all of it would be spent on the frequency shift. So I think it's an interesting idea that it connects dots, it connects several dots, but at the same time, I'm not sure how you would power something like that.
Yeah.
So that's my thoughts on it.
Well, thank you. Let me go to Jeremiah Pop next.
All right, thanks. Yeah, I had a question about using iron, because we've noticed some interesting things about the refractive index of iron and its permeability. It's a strange phenomenon not often talked about, but as you get closer and closer to absolutely pure iron with no inclusions, you know, if you get like 99.9%, it's got a reasonably high saturability, but if you start to get into the 3 nines, 4 nines, it goes way, way up, and it starts to exhibit unusual properties. And so the reason I ask is you mentioned iron in one of your slides, Effie, as one of these possible materials where you inject one kind of wave and you get an emission of a different kind of wave, which appears to have some kind of a different vector to it. And so I was wondering, you know, have you ever heard of, or are you familiar with NMR and DNO? Nuclear
I'm
magnetic
not.
resonance and dynamic nuclear orientation?
I'm not.
Well, basically, I think I have a postulate regarding iron, and because it is so dense and because it has such a huge number of electrons in its valence, its magnetic moment could be, if aligned, tremendously large. And as a result, the amount of energy that you could potentially have surrounding that iron atom with its electron valences being perturbed, consequently influencing its protons being perturbed, basically dynamic nuclear orientation, the total stress energy surrounding that iron atom to become significantly higher than that same iron atom in a just standard gravitational field not being influenced by electromagnetism. And so it may explain some of the strange refractive index properties, and perhaps even have something to do with gravity attenuation if driven or resonated correctly. And I'm just wondering if, you know, why specifically you referenced iron in one of your slides. You know, if you could talk a little bit more about that.
I'm not hung up on iron. It has to be, if you go through the equations of this model, permittivity, because you can't get large values of it in nature, doesn't really have a large effect. Conductivity has a huge effect, so you're definitely going to pay attention to that. And permeability is the other guy that has a huge effect. So the idea that we started with was try to get the permeability as high as you can in order to get the MG equation to reduce mass. In other words, the higher the permeability of the material you're working with, the less energy you need to create the mass reduction effect. So having a high permeability reduces the amount of illumination you would need to see that effect. So that's why we talk about permeability. I just chose iron because it's something people know a lot about. My experiment, I used supermalloy, which is a ceramic iron.
May I ask you just real quick? I'm sorry to disrupt, but I have been searching for supermalloy tape, very thin. It's extremely hard for me to find, and I can't seem to acquire it from anybody unless I'm buying a massive spool. Is there either, I mean, if you have a resource for that, I would very, very much like to find out what that is and get some.
Yeah, I'll say a few things about that. First of all, supermalloy is a ceramic metal, and because of that, it shatters into micro shards. So it's a health risk. You don't want it in your eyes. You don't want it in your body. You don't want to handle it with bare hands. So when you work with that stuff, you really need to be vigilant about what the material is. And of course, you can't bend it, or of course, you know, if you bend or flex materials, the permeability is reduced because you're destroying the crystalline structure of the material. So first of all, I want to caution you if you ever work with that material. Secondly, I worked in the smart grid industry for 10 years. I developed some technology for that. And as a result, I became friends with a transformer engineer in Mexico, and he supplied me the cores. I would be more than happy to supply you one. What you would get is a plastic bobbin that you'd have to take the core out of it, and you have to be very careful when you do that to keep from breaking the core. But I'd be more than happy if you email me at sburns808. I'd be more than happy to send it to an address you send me to.
I will absolutely be
but-
sending you an email. If you don't receive it by the end of this conference or within several minutes, it means I must have gotten your email address wrong. So feel free to send me it in the chat just in case. If you
Okay,
can,
I'll work
mind. Thanks. Thank you so much.
I'll work through Tim if I can't get it. And I agree with you, it is hard to find.
Well, let me do this. Jeremiah, thank you. Let me jump to Sean Logan because he hasn't asked a question. He's been patiently waiting, and then I'll come back to Jeremy. So Sean, go ahead, sir.
Thank you for your presentation. My question is there a particular type of transistor or tube that you're using in your amplifier that works particularly well for a low frequency, such as 0.1 hertz? And my other question is, do you need or are you using an impedance matching network between your antenna and your transmission line?
Yeah, those are good questions. I always like to drive a antenna with a balun because it makes it it floats the antenna basically. I'm not using that in my effort right now. I'm just taking the antenna and I'm using it as a series resonance circuit. And so if it's an inductive loop antenna, I've got to add a series capacitance to it. If it's a dipole, I've got to add a series inductance to it. And I'm just getting it to the point where it will resonate. If you go through the math, you'll find out that if you have a dipole that's 1 nanofarad, you'll need, I don't know, 10 million henries of inductance. If you have a loop antenna that's, say, 10 millihenries, you'll need 10 farads of capacitance. So what I've done is I created a simulator to actually amplify capacitance and amplify inductance. And I covered that in my first presentation. You might want to go back. I actually showed you some circuits. So what I do is I use op amps. We're working with low frequency, so there's really nothing special about the op amps. I selected them to deliver a high power. They're chopper amps, so they're high efficiency op amps that can deliver amperes of current, and at a fairly high voltage. I can get up above 50 volts, and they give a pretty good representation of the sine wave that I'm working with, and I can actually experience the resonance and so forth. So to answer your question, I would like to float the antenna, but at the frequencies I'm working at, I don't want to get involved with an antenna transformer core. So I'm just driving them directly as series resonance. And then I'm trying to come up with a either capacitance multiplier or a inductive gyrator to deliver the high capacitance or inductance that I need to form the resonance. And you have to actually spend some time with these circuits because in order to get them to deliver the currents, you have to do all kinds of tricks with them. So I really haven't published anything on that in detail other than to say that's how I'm doing it. So that would kind of be another presentation if I was going to go into detail on that. but there's nothing special about them other than they're high current chopper amps and high voltage. That way I can get, you know, the power I need to deliver to these devices without having to go through a lot of discrete design. I'm hoping that answered your question.
Wonderful. Thank you again, Sean. Let me go back to Jeremy Reese now, and then we'll go to Karl after that.
Hey, Steve, could you just reiterate your email? It was sburns808@yahoo.com.
Yes. 808. It's 808.
All right, cool. All right, I just wanted to reiterate that. There's maybe a few people that want to get a hold of you. So you mentioned Balun. That's a BALUN.
Yeah, BALUN. Balun stands for
Balanced.
balanced, unbalanced.
Yeah, unbalanced.
And so what it is, it's a way that you can float an antenna without having it connected directly to ground. And what that does is it allows the antenna to do whatever it needs to do to adjust to the drive. And so it's a pretty common thing in antenna theory to do that. I'm not doing it here just simply because I really don't need to make the measurements that I'm doing, and it adds another layer of problems into what I'm trying to do, and I just don't want to go there. If I was actually going to try to do this on a larger scale, I definitely would want to do something like that. Another choice would be you could float the electronics. So
Right, have no ground. Well, that's what you'd be doing on a craft, right? There's no ground on a craft. You're flying.
Yeah, you'd be floating electronics so that you basically really wouldn't need the Balun. The only way I would consider transformer coupling is if you had to go through a barrier like a wall.
So what would we use on our craft? How are we going to design this thing, man?
Well, you know, my wife keeps telling me they don't even exist.
No, we're going to build one.
Well, we're going to build one. Well, what I'm going to do is I'm going to go with a cigar, simply because I know for sure where the resonances are because they're published. And what I would have to do is I'd have to slow the phase velocity in the antenna material so that the cigar would become a half wavelength at 1 hertz. That's a really slow phase velocity. You've got to slow it way down. So if you make the antenna superconducting, you can use the sigma of a large superconductor to help you with that. You might be able to use metamaterials to slow phase velocity. I haven't explored that. That was something that people are suggesting.
Well, there's this idea in the theory that it's transmuted much better via the surface of objects, via what are called surface plasmons. And there's been some interesting, research that's been done with just, grid-like structures tend to transmit these signals much better, especially if the grid is spaced at the wavelength of the to match the frequency.
Yeah. Well, this model is pretty cut and dry. It basically just says you've got an antenna that's got really slow phase velocity, so it's an efficient radiator.
Yep.
And then basically all you have to do is connect a sine wave to this. But if it's resonant, you don't even have to tune it. You just take a sine wave oscillator, connect it to the antenna, you're good to go, as long as you can deliver the power to it. If it's more sophisticated than that, like you have to tune the antenna, then you would need some kind of tuning circuit like I talked about. But at any rate, all you'd have to do is just connect it directly to the shell of the craft and power it up and drive it with a sine wave, and you're good to go.
And this is what our engineering team insists is going on with this Alexey Chekurkov device, which we're going to talk about next here in about 15 minutes. Yeah, this is awesome stuff, man. Steve, thank you so much for taking the time with us, and I'm going to hand it off to the next person, Karl.
Yeah, Karl, go ahead, sir. And actually, Alexey, that's a couple hours out because we're going to hit the SCU as well and have Rich and Peter Reali speak. But Karl, go ahead, sir.
Thanks very much, Steve. Can you guys hear me okay?
Yeah, you sound great.
Fantastic. Hey, Steve, how similar is this to something like Thomas Townsend Brown and his ideas for using antennas for mass reduction?
I don't know the answer to that. My guess is that there's a lot of theories out there. A lot of them use ideas that are similar to this, but they don't have the fundamental quantum mechanics field theory that drives this model. So my guess is it's going to be different. There's a lot of effects out there that some of them are known, some of them are just assumed. This effect is assumed. No one's proven it yet, so, which is what I'm trying to do. But at any rate, my guess is it would be different. And I'm not familiar enough with the work to tell you the exact differences, but it would surprise me if there was a lot of commonality in it.
Thanks so much. I really enjoyed your presentation.
Okay, sorry about that. Did you guys wrapped up the question? I had to step away and use the restroom really quick. So who should we go to next? Who has questions for Steve? Jeremy, did you have anything more?
I have something.
Oh, okay, go for it, Mark.
No, I don't.
Okay, so we have an experiment that we're actually in the middle of working on, which sounded a little similar to what you were talking about. Basically, these two plates are antenna, and we're going to be modulating them at the frequency of the radius, either that or half wavelength or quarter wavelength of which. This is way up in the gigahertz range, about 2 gigahertz for the wavelength over here. And we're also going to be separating it from another plate at the same wavelength. And there's going to be a capacitor in the center so that we'll be able to charge up the plates to have both standing waves and high voltage, and see if there's any effect. Does that tie into your theory at all?
It doesn't. You know, if you work in the gigahertz and you go back to my presentation where I talk about energy per cycle, the amount of energy you would need per cycle at a gigahertz would vaporize everything around it to make this model work. That's why we're using low frequency. So basically this model, it just says if you can provide radiation that has a certain energy per cycle to an atom that can respond to this, that it will have this effect of space refraction. There's really just nothing else there. It's just all that it is.
You should also look at the work of Frederick Alzafon. It's another experiment that we're working on. It sounds very similar with dynamic nuclear orientation, or EPR, electroparamagnetic resonance, using the valence electrons to orient the subatomic particles in the core of the atom, supposed to create some sort of anti-gravity effect.
Yeah, you know, MRI does a lot of that. MRI is amazing if you read how it works. I think it's the pinnacle of nuclear engineering. I'm not saying that none of that is relevant. What I am saying is that if that's happening in this model, it's happening internal to the atom during the process of this model, and the model really doesn't address that. So I can't really tell from this model details about exactly what the atom is doing. And what you're basically saying is, let's engineer atoms to do specific things. All this model says is that if you radiate them, or if you cause them to radiate, they'll do it. So it's hard for me to connect the dots between that and specifically what an atom is doing internally, especially if you enter quantum theory. it's not something that could even be intuitive. So the answer is I just don't know. I'm not saying that it's not part of what this model is doing. I'm just saying I don't have the ability to connect the dots.
Okay, also, with your antenna contraption that you're working on, if you need any help putting it together or something like that, we do have a CNC machine here at the lab in Hawthorne, New Jersey. So we could help you out with custom parts.
Well, I would really like to connect to that. You know, I'm just doing this in my man cave as a hobby.
I mean, that's pretty much what most of APEC is about. It's about
you
the
go.
man cave hobby, and we're trying to make it, more serious. And
Yeah, no, well, I'm on board. I'd really like to connect to that because from time to time I do need stuff, and I have quite a bit of material too. I have superconducting wire that I can't use and other things.
we got liquid nitrogen back here.
Yeah, well, I wish I had that. I would almost send you the wire just so you can play with it. But at any rate, yeah, I'd like to get that connect. It'd be great if you could email me and give me a link to that.
Where are you based out of?
But pardon me?
Where are you based out of?
Oh, I'm in North Carolina. I'm just at my house in North Carolina.
Oh, that's right next to Todd. You should meet up with Todd.
Oh, okay.
That's the auto.
Well, I'm outside of Raleigh.
I would have to check his address, but he's North Carolina. It's not that big. Bigger than New Jersey.
I'm jealous of all of you because in Seattle our weather changed. We're into that rainy season now, so it's just bleak. You guys still have nice weather.
Well, Tim, you used to have a man cave lab working on the ion craft, right?
Yes.
That's how you got into this.
I did. Yeah. Once upon a time, I didn't have a lot of Steve's stuff though. He's working with very different machinery, right? With ELF stuff. So it's not, Steve, if I understand correctly, it's not the super high voltage. And like the other thing I remember was when I was looking at De Aquino's ELF, what was it? There was an iron core radiator that was like basically 100-pound iron ball, wasn't there? Something like that. It was massive. That was where I remember last time I looked at it. Maybe that was System G, but it's heavy duty stuff, and a lot of the ion wind stuff we were playing with was very light. So it's kind of a different world. Well, if it's okay, let me go to Jeremiah, who's being patient over there, sir.
Yeah, I'll try to keep this quick because I know we're running out of time for the end of Q&A. I was just going over JLN's site of his attempted replication of one variant System G, where he's got the two what look like plastic coated cables, red and blue. Looks like they're counterwound, so those are his two ELF antennas, surrounded by some fairly coarse grain iron powder. Ideally, it'd be fine grain, but whichever. I'm wondering, first off, have you seen that replication of his? And in your opinion, do you think that it was a faithful test of what you're proposing?
Yeah, I talked about this in my first presentation. I worked with De Aquino for about 4 months. We emailed each other every day. He even emailed me on Christmas Day. And so we were really into it for several months. And we came up with systems A through H. Systems A through F, we discarded as the learning curve. System G basically tries to use a less conductive medium with a really highly conductive antenna so that you don't basically just short the antenna out. So here's what I can tell you about System G. I have several emails from De Aquino in my archives where he claims it was working. I've never seen it. All I've seen is pictures of it. Excuse me, drawings of it. I've never seen a picture. I've just seen drawings. But his emails claim that it works. He goes to some of the designs. The one big problem I have with it is their transformer. It's a solid iron rod, and they're drawing high current out of it. And inductive transformer engineers will tell you that that would heat up red hot in no time because it's not laminated because of hysteresis. So I have a big question about the transformer they're using. It doesn't make sense to me. So that leads me to believe that maybe it was just somebody trying to get people to do their lab work for them. I don't know for sure, but I can tell you this. He told me that the antenna was designed in a consulting firm in the Southwest United States. I didn't get a name. It was supposed to be naturally resonant. I'm suspicious that iron filings will work at all, and the reason is I think there's too much air. If you add air into the medium, it becomes a major factor of what you're doing, and it's not friendly for radiation efficiency. So I'm skeptical that that experiment would even work.
Yeah, it's sort of like the iron probably short out too. I mean, not only is it a conductive loop that's gonna somewhat cancel out the fluxes, which I guess might be ideal, you know, assuming the two antennas totally cancel their beat fluxes in the near field, but it's almost impossible if you're using any kind of conductors with thickness. So yeah, maybe something like a powdered iron in a medium where the pieces aren't physically touching, an extremely fine grain, you know, ultra small particles where basically we can get rid of almost all the air and we can fill the rest with some kind of a dielectric, just so that we don't have any of those gaps and we have good coupling between all of those particles. Might really help.
Yeah, you're on track. Yeah, so that's the game you're playing, is trying to figure out how to use Maxwell's equations to say this thing will radiate, and the higher conductive of the medium, the more it's going to radiate. The problem is you short out the antenna. So if you have a superconducting antenna, you can keep that conductive range between antenna element and medium orders of magnitude apart. And now you have a way of having a high conductance around the antenna without shorting it out. But go ahead.
One last simple question though, and I mean, maybe this will probably just answer a lot of my other questions in terms of the complexity. Is this system basically taking advantage of the high permeability of the surrounding ferrous materials to increase the refractive index so that you can build up a significant stress energy tensor in and around the coil?
Yeah, so now you're on the relativity side of this, and I think that's correct. Basically, this model doesn't tell you anything about that. It just tells you how to do that. And you could very well be increasing the energy around the space of this thing. You know, that's why it would be nice to have a calibrated refractive index instrument where you could do experiments like this. So I think the answer is yes, that's absolutely feasible, and it's actually likely. So I think that's probably on track with what you're saying.
That really helps, Steve. That really has helped. I appreciate everything that you've said so far, and again, great presentation this time. I loved what you had to say last time, and was so pleased to see you on again. So please continue your work, and I can't wait to get in contact with you. I did send you that email, and we would love to work with you and maybe help you along and get some things moving here, because it's time to get the experiments going. It really is.
Well, what I like about this model is that if you can get it to work, it virtually changes everything we know.
Wonderful. Okay, well, thank you, Jeremiah. And Steve, thank you again, sir. So yeah, we only have about 5 minutes left with Steve. And again, I want to thank you for your time. Does anybody else have any last minute questions for Steve Burns? Okay, well, Steve, again, I genuinely cannot thank you enough for joining us. So let me do this. I want to put this on gallery view. And again, we've got about 5 minutes left here. But everyone, please put your hands together and give Steve Burns an enormous applause for a wonderful presentation and detailed Q&A session. Steve, thank you. I know that was a ton of work. And again, this is incredibly detailed information. So
yeah, I appreciate you giving me the opportunity, Tim.
Oh yeah, absolutely, absolutely. We love having you on. I mean, this is
I mean, I think you're a national treasure bringing these groups together.
Well, I appreciate you saying it, but all I'm doing is playing traffic cop. It's you guys are the ones doing all the work. So.
The Japanese were causing a bit of a nuisance in the.
Sorry. Okay, I had to mute Mike out there. Okay, so let's do this then. We've got about 5 minutes left, and do you guys want to take a quick break, or should we go to, next up, we have Peter Reali and Rich Hoffman from the SCU.
Yeah, I'll do a bathroom break, everyone. We can stay and chat for 5 minutes, I guess. And yeah, I just I think the metamaterials and this so I shared this one site with my chat. I was looking up balance because I'm trying to remember how to spell that, because I had heard of them before and I wanted to share that with the chat. So I had looked it up and I found antennatheory.com. It's antenna-theory.com. And they have a whole page on balance and the theory of balance and a couple different types of balance, including a bazooka balance.
And again, Jeremy, you were saying that's I believe Steve said that was balanced, unbalanced, and he was saying that it lets the antenna float kind of and do what it needs to do. So
yeah, but we don't need that for our craft because we won't have to worry about the grounding issue. So we'll just need I guess a dipole antenna.
Yeah.
So how would we build this antenna for the craft on our craft, and how would we drive it?
Oh, William Schramm had a question. We have a couple of minutes left here. Let me go to William here. William?
Yeah, I just wanted to throw this out for discussion. I hope you guys can all hear me. The question is, with any of these levitation techniques, how much power is required? And do we have a means of driving that level of power? So if Steve Burns' solution works, do we need a reactor core to drive this, or could it just like a turbine or a natural gas engine, something like that? Could that drive it?
A couple AAA batteries.
Right. Yeah. Is that all it takes? A 12-volt battery?
I think any of these are going to take considerable energy, and actually, I'm sorry that we weren't able to ask that when Steve was answering questions. He's still with us. If you want to pop on and answer, that's fine. But
for my website no longer has downloadable papers because Google undid the site's platform, but one of the papers I had on there was a design of a gimbal that was 30 foot long and 5 feet high, and it took about 1 kilowatt, and that's all it took. But again, it depends on frequency. The lower the frequency, the less the power you need. So I was operating this at about 0.5 hertz, and it was taking about 1 kilowatts. And like I said, if you go up to 100 hertz, you're going to end up with 1,000 times more power requirement. So that's why we're using ELF. And if you keep it below 1 hertz, you can keep the power required for a 30-foot craft under a kilowatt.
Okay.
Awesome.
So
thanks again.
To give McCandlish's design then some credit, this could be a hydrogen fuel cell fueled craft.
Yes, as a matter of fact, I point that out in the paper that I was doing this on, that the fuel cell could power this.
How about solar power?
No.
There's a thousand. Well, no, there's 1,000. Basically, there's a kilowatt per square meter coming from the sun. Our efficiency is pretty low at converting that into energy, but the power is there. Is my point. That's just like floating out there in the sunlight. So if you could do it for 1 kilowatt, I don't see why you could use the sun.
Okay, and on that note, let me mute everybody out. Well, no, and again, Steve, thank you very much. I'm going to mute all. Okay. And I want to do a brief introduction for our next guest because it's 2 o'clock now. So